Do we have, questions from the quiz? Anyone?
So for the first one, we have to write the equation.
For the first one, you have to write the equation.
Like the formula.
Yeah, the formula. Yeah. Anything else? Are we okay with the sig figs on question number 1?
Oh, also for question number 1.
Yes.
A negative, but it has to be positive.
No, it's okay. I accepted either. Yeah. We good? Okay. Yes. Is the blue book going to be on the quiz? No. Blue book is not on the quiz or the test.
What is it for?
It's for AP. It's all the stuff that is in AP but is not in regular 12. That's why it's called AP Extras. Does that make sense? So green. Pardon me? Well, we did one of the sections already. We've done spectrophotometry. And as soon as we finish up section 1.4, we're going to move on to 1.5. Oh, no, as soon as we finish 1.5, we're going to move on to 1.6, which is in the blue book. Yeah? What 1.5 is what we started on Friday. That is kinetic energy diagrams. So do we remember about kinetic energy diagrams? That was on we left off on page 106. So, just for a moment, if I draw a curve, actually, just put your finger in that place and then close the book for a second. Okay? And I want you to, in your head, think what that kinetic energy diagram looks like. What is the general shape? Show your partner. Just draw it with your finger on your desk or something. Where should it start? 0, 0, 0. What is the x-axis? Okay, we'll come back to that. What's on the y-axis? Number of particles. What's on the x-axis? Kinetic energy. And it goes up first. And then we get a peak. Should it be symmetrical? No, what should it do? It should have a right tail off. Okay? It should approach but not reach 0. Because that is an asymptote. Theoretically, you could have an infinitely fast particle. Whatever. All right, now, how would I draw an activation energy on this curve? I would just draw a vertical line. If I asked you to shade the area representing the collisions which are successful, where would you shade? To the right of the line. So these are the successful collisions. I'm just going to put successful collisions. And we have over here, we have the unsuccessful collisions. Now, we didn't get to this last day, but what would happen to this curve if we were to increase the temperature? Ooh, before we do that, what does the area under the curve represent? All the particles, the total number of particles. Will that change if you increase the temperature? No, this stays the same when you change the temperature. So the area under the curve stays the same when you change the temperature. Where would I find the most particles? The most particles is at the peak, okay? So that is right here, this is the kinetic energy. This is the most probable kinetic energy. So I'm going to now redraw this so it doesn't have all that writing all over. Well, maybe I won't. No, I won't. We'll just go with it. I'll make it blue. Okay. What's going to happen to this curve? What's going to happen to the most probable kinetic energy if we increase the temperature? What will happen to the most probable kinetic energy? Will it stay the same? Will it move to the left? Will it move to the right? It's going to move to the right. Okay, so that's our peak. What's going to happen to our lowest kinetic energy? Right now, the lowest kinetic energy is 0. If we're at a higher temperature, what's the lowest kinetic energy? 0. Okay? No change. Up here, up in this area, we have our fastest particles. What's going to happen to the kinetic energy of the fastest particles? Are they going to stay where they are? So is that curve going to end at the same place? Is it going to end further to the left? Is it going to end earlier, or is it going to end later, further to the right? It's going to end further to the right because the fastest particles will have more kinetic energy. So far, so good? Okay. So we have our curve now ending further to the right, somewhere over here. We have it starting at the same place. We have the most probable kinetic energy moving to the right. What would the shape of the curve look like? How would the height of the curve be? Would it be the same? Would it be higher? Would it be lower? Has to be lower. Why does it have to be lower? Explain to your partner. Higher, lower, same. What do you guys think?
The height will be lower
The height will be lower. Why?
because all the particles are shifting to the right.
All the particles are shifting to the right, and the area under the curve must remain the same. Okay, so here we have our lower temp. Or sorry, not lower temperature. What am I saying? That is our higher temperature. And if we were to then shade the area for that one, where we have effective collisions, we now have a larger percent or a larger fraction of all the particles have sufficient energy to react. Does that make sense? And that's all there really is to these curves. Okay, you can change the activation energy, like if you have a catalyst, the activation energy gets lowered. You can change the temperature. Nothing else really affects the curve particularly. Okay, so let's just go back and see what was in here. The effective temperature on a kinetic energy curve. So you can see this is on page 107. So we have our low temperature, we have our medium temperature, and we have our high temperature. And although these actually touch zero, they shouldn't really be touching zero. This is our highest energy particles. What's the label on our x-axis? Kinetic energy. And what's the on our y-axis?
Number of particles.
Number of particles. Curve gets wider at a higher temperature because the area has to remain the same, because the area is the number of particles. Key points. When temperature is increased, the peak moves right, the peak gets lower, and the curve gets wider. And vice versa when the temperature is lowered. When the temperature is lowered, the peak moves left. The peak gets higher. And the curve gets narrower. Is good? Yes? Narrower or wider? Okay, so the area under the curve has to stay the same, yes? So if I have, let's say I've got a 3x4 grid here, yeah? 3 by 4. That gives me an area of 12. If I make the base wider, say instead of 4, it's now 1, 2, 3, 4, 5, 6, then in order for the area to stay the same, the height has to get lower. Does that make sense? Cool, cool, cool. So this now just goes into a little bit more depth, just showing you how you get at the higher temperature, the proportion of particles with sufficient energy to react is greater. And we could play games where we figure out the percentage. I don't know. This one, I would say this is about, I don't know, 1/10. This one, I would say it's about 1/3. So that would be 0.1. This one would be about 0.33. So 10%, 33%. So as temperature increases, the fraction of collisions, stop doing that. Why are you? There we go. The fraction of collisions with sufficient kinetic energy to react increases. So that's where one of the ways you can justify that claim, or instead of fraction, you could say percent. Kinetic energy curves and catalysts. Here we have our activation energy without a catalyst, and here we have our activation energy with a catalyst. And maybe according to this, I don't know, I've got maybe 1/10. So that's without the catalyst. And then with the catalyst, maybe it's 1/3. I don't know. I could totally be exaggerating. Maybe that's like 1/5 or something, but it's certainly less. You know what I mean? Yeah. So you should be able to, given a curve, you should be able to show it what happens if it's at a lower temperature, what happens if it's at a higher temperature. If you're given an activation energy, you should be able to say, if that is the uncatalyzed, where would you put a catalyzed activation energy? And the catalyzed EA is further left. At a lower kinetic energy. Alrighty, and like I said, there's not much more to it than that. It is a good review of Maxwell-Boltzmann diagrams for gases as well. So there we are. There's some exercises here. We're not going to spend any time on that, though. We are going to grab our blue books. Woo! Oh, before I go on, does anyone have any questions from the review? The reaction rates review.
Question 46.
46.
Page 12.
Any others? Ooh, has to think hard. Okay, paste. There we go. Computer's getting old. Has to think a lot to do these things. Okay. No one else has any other questions? Just number 46? Okay, well, we'll do number 46 then. Number 46, we have a two-step reaction mechanism. Which one of the following changes would result in the greatest reaction rate? This is on page 12, if you're looking for it. Now, which of these two steps controls the rate? Step 1. That is our rate determining step. That's our RDS, rate determining step. So which step do we need to speed up? We need to speed up step number 1. What is one way you could speed up step number 1? You could increase the temperature, but that's not one of our options. We could increase the concentration. So we want to increase the concentration of something that will speed up step 1. What will speed up step 1? NO2. You need to increase the concentration of, yeah.
That's like my biggest question. Why is it too?
I could write it like this instead. Doesn't matter.
Because I was looking at it and then I was trying to kind of cancel it out. Like it just seems that like the NO2 cancels on both sides.
Oh.
Yeah,
I see why they've done it that way, because it is also a catalyst. So this is a self-catalyzing reaction. Right? Because you've got it going in and coming out. But NO2 is also, because the other one doesn't cancel out, it is also just a reactant. Yeah? And then we have an intermediate here and an intermediate here. And so our overall reaction would be NO2 plus CO goes to NO plus CO2. That's our overall. And it's catalyzed by NO2. Yes? No.
So how do we know if
How do you know it's a catalyst? Because it cancels out. If it cancels out, if it's on one side and the other side, either it's a reaction intermediate or it's a catalyst. Okay, so the two things that cancel out.
So would NO2 be the reaction?
Yes. So the two things that cancel out, one, reaction intermediate, and 2 is the catalyst. And what you're looking for is for the reaction intermediate, you're looking for something that is here. No, I'm sorry, wrong one. You're looking for something which is here and then here, right? For a catalyst, you're looking for something which is here and then coming out later. So that's the difference between them. Is good? Cool. Any other questions? Okay. Any other questions from any homework, from Hebden, or anything else before we move on to our blue book? Blue book it is. Okay.
But
Yes.
was asked.
Ooh.
Oh, so like there's like one of the questions that includes like concentration, changing concentration for like the kinetic energy. So
Oh, for the kinetic energy diagram, yeah. It would just get bigger. So if you had a kinetic energy diagram, this I think was one of the ones. If that's our normal curve, number 64. Okay. Number 64. So here we have our diagram here. And 64 says, what happens if we increase the concentration of the reactant? Our most probable temperature should stay the same. The ending area of the curve should stay the same. Just everything should be
because you're adding more parts.
bigger. Like this'll come down like this. Do you know what I mean? Everything should just be bigger. So out of our choices there would be no change. The activation energy does not change. The peak decreases in height and moves to the right. What?
There is no change.
I guess there's no change. Oh, because this is the fraction of particles with a specific energy. It's not the total number of particles. That's why there's no change. So when they say the fraction of particles with a specific energy, now you're looking at a percentage of particles with a specific energy. So it's everything per 100. Yeah? So now it's a ratio, and now it's no longer a number that can get bigger or smaller. The total percent will always be 100%. Okay, so the area under the curve is 100%, or 100 out of 100 is the fraction, the total fraction. Does that make sense compared with, like, if this over here was the number of particles, then the peak would get higher and the whole thing would just get bigger. But because it's the fraction of particles with a specific energy, the height of the peak doesn't change. So the total area is 100 particles out of 100 particles. But if we said, what's the fraction of particles with sufficient energy, you'd be like, okay, this right here, that looks like, I don't know, 1/20th. So that would be, what's 1/20th of 100? 1/10 of 100 is 10, so it would be 5%. Okay, does that make sense? Okay, cool. Don't get too wound up about it. It's okay. You're probably not going to get much in the way of questions like that. Yeah. 87. Okay, so we have H2 plus Br2 gives 2 HBr. What can be said of the relative rates of consumption of the reactants when compared to the rate of formation of the product? So we know that we have coefficients of 1 and 1 and 2. So we are making 2 HBr for every 1 BR2 used. Yeah? Okay. So is it true that HBr will be produced at half the rate that bromine is consumed? Is that true? No. Is it true that HBr will be produced at the same rate as bromine is consumed? No. Is it true that Br2 and H2 will be consumed at different rates? No. HBr will be produced at twice the rate that bromine is consumed. Yes. E, it is not possible to tell anything about the relative rates of consumption and formation. No, rates react stoichiometrically. Yeah? Is good? Cool. Anything else? Okay. AP extras. All right, we made it through 1.7. We're going to do 1.6. Introduction to rate laws. This is on page 1. Page 1. For a general reaction between reactant A and reactant B at a constant temperature, we can represent the small letter A to be the coefficient of reactant A and the small letter B to be the coefficient of reactant B. So A plus B gives products.
Wait, is this something else?
No. Blue book not on test. Blue book not on test. No. I'll give you practice material, but I won't give you a test on it. Not unless you want one. If y'all are like, yes, please, we'd like a test. But we don't really have time to write it, so we will, you'd write it after school. And we can do that if you just like a little practice sit down, I don't want to just take it home, I want to actually sit down and practice, writing something, I can definitely do that for you. Okay? All right, now, rate increases as reactant concentration increases, but by what factor? Rate can be represented by A to the M, and it's proportional to A to the M times B to the N. And do you notice what these are not? These little numbers here are not A and B. So in other words, they're not the coefficients. And the reason I bring this up is because in Unit 2, we spend a lot of time raising the concentration of A to its coefficient. But that's a different unit. That's equilibrium. This is reaction rates, and in rates, we never raise concentrations to their coefficient just based on the coefficient. Sometimes it will be raised to the coefficient, but you have to determine that through other means. You can't just say, oh, I know the coefficient. I know what power to raise the rate to.
So what are
They are things that have to be determined experimentally. Okay? So you should be familiar with this equation. This is the rate law equation, and it says that rate is equal to K, which is a constant, K for constant, times the concentration of A raised to the M, B raised to the N. K is a constant. And it is known as the rate law constant. it is different for every reaction and it is different at every temperature. Okay, so it's not very constant, but if you have the same reaction at the same temperature, K will always be the same. So the rate constant, actually I shouldn't say the rate law constant, I should just say the rate constant. Rate constant. Let's get rid of law. It varies with temperature, which is why at different temperatures you have different rates. Okay, the exponents m and n are constant with temperature. If you keep the conditions constant, like if you aren't mucking about with the temperature, the rate constant stays the same. Exponents m and n can only be determined experimentally. They are not the coefficients in the balanced equation. And you'll notice, how many times have I said this now? They are not the coefficients in the balanced equation. The values of m and n can be determined only through experimentation. They may or may not be the same as the coefficients. If they match, it is only by coincidence. The exponent values are usually 0 or 1 or 2, but maybe 3, or in some cases they may even be fractions. Okay? Now, there's this thing called the order of the reaction. Oops, that seems to not be working. Let's grab the one that does work. Order of reaction is determined by the exponents. And it's really easy to say what the order is. You're going to have first order, second order, third order. Okay? And actually there is a 0th order as well. 0th order. So if we have an exponent which is 1, then we have first order. If we have an exponent which is 2, guess what order it is? Second order. Shocking, yes? And if you have more than one reactant present, you take the sum of the exponents so m plus n, and that is called the overall reaction order. So if our rate law had A to the 1 and B to the 2, the overall order of the reaction is equal to 1 plus 2 is 3. We can also say, what is the order with respect to A? What is the order with respect to A? Take a guess. Yeah, first order with respect to A. WRT means with respect to, with respect to. So we are first order with respect to A. What order are we with respect to B? Second order. So if you start thinking about what these numbers mean, if you had a first order equation, that means that as the concentration of A increases, the rate increases linearly. Yeah? Because it just goes as concentration of A increases, the rate increases, and it doesn't go as the square or anything fancy. So that's going to be a linear increase. But if you have a second order equation and you have rate is equal to A concentration of A squared, that means that as rate as concentration of A doubles, the rate is going to times by 4, 2 squared. Yeah? If rate triples, if concentration of A triples, then the rate is going to go 3 times 3 is 9. So it's going to be 9 times as high. Okay? So that's what the orders have to do with, is how, like, what the shape of the graph is going to be. Is it going to be linear? Is it going to be a square? Is it going to be a cube? I don't know. So here is reaction 1. Experimentally, the rate was found to be first order for N2O5. The rate varies directly with N2O5. That means it's going to be linear. And we can write the following rate law. Remember, rate law, you always have 3 things. You have rate, you have the K value, which right now we're just going to write as K, and then you have whatever concentrations you may have raised to whatever power they are raised to. So that is called the rate law. For this reaction. No. Does the rate of a reaction depend upon the concentration of the product? Does increasing concentration of product cause any more collisions between reactant particles? No, so concentration of product does not matter. So in this reaction, we know that it's only going to be dependent on the concentration of N2O5. And the only question then is, what will the exponent be? And we're told in the question that experimentally they determined that it was first order. So we can put an exponent of 1. And you'll notice that that exponent of 1 is not the same as the coefficient. It is different. What is the overall reaction order? Not hard. 1. Overall reaction order is still first order. Okay, here's reaction number 2. We've got NO2 plus CO gives NO plus CO2. So this time we have 2 reactants. This one was found to be second order for NO2, and it is found to be 0 order for CO. So let us, I'm not going to show that part yet, we're going to write the rate law for this one, for this reaction. What's the first thing you write in rate law? Rate. Rate equals, what's the next thing you write? Constant. And then, what else do we write? Concentration. So we got NO2. What would its coefficient be? Or sorry, not coefficient, exponent. It would be a 2. And because we now have another reactant, we're going to put CO 0. Could we simplify this?
CO 0.
Yeah, CO to the 0 is just equal to 1. So we could say K NO2 squared. So what that means is that this particular reaction actually doesn't change its rate when you change the concentration of carbon monoxide. You would not be expected to know that unless somebody tells you that it is 0th order for CO. So anytime you're like, if I said, how could you speed up the rate of this reaction, in the regular material, you would say, I could increase the concentration of NO2, or I could increase the concentration of CO. You would not be expected in any way to know that it was 0th order for CO. Does that make sense? Like, this is like outside the realm of normal stuff. So just pretend you've never heard of it when you're dealing with normal stuff. Yes? Have different boxes in your head. Have the box for regular chemistry, and then have the box for rate law. Yes? If it doesn't say rate law, if it doesn't ask you anything about rate law, and it just says, how could you increase the rate of this reaction without having any other information about it, you can't, they couldn't say you're wrong for saying increase the concentration of CO.
It does tell you.
If it does tell you that it's 0th order with respect to CO, then you would not be able to change CO. Does that make sense? You have to go with the information that they give you. Chances are they're not going to give you anything that confusing though, right? Okay. So here's our rate law. It can be simplified. Notice that, again, how many times am I saying this now? The value of the co-exponents are not the same as the coefficients. The overall reaction order is 2nd order. 2 plus 0 is 2. Reaction 3. We have one reactant. Experimentally, we've got 2 HI, so we only have one reactant here. Experimentally, the rate was found to be 2nd order for HI. So this means that the rate varies directly with the square of the concentration of HI. So if we double concentration of HI, the rate will go by times 4. If we triple it, it'll go times 9. If we quadruple it, it'll go times 16. Okay? And our rate law then is just rate is equal to constant times HI squared. There's our rate law. Woo! Where'd we go? How did we jump back that far? Okay. Oh, why did I write that? That's silly. The value of the exponent is the same as the coefficient for HI in the equation, but this is a coincidence. Okay, and I need to fix this. Oh. Why do all I need to do is get rid of this? Because I've written it here correctly. Why do I have both? I don't know. Fix. All right, so there's a few little exercises here which you guys are going to do right now. You are going to write the rate law equation and the overall reaction order. Give those a try. You can check your answers at the bottom of the page if you like. Make sure I haven't made any mistakes.
On the exam, would they prefer us to write like the coefficient of 1 next to the concentration, or just leave it out?
Either way is okay. Yeah, it doesn't matter. Like Olivia was asking, do we want you to write the coefficient of 1? You can, but you don't have to, okay, because 1 is implied. Yeah. Alrighty, are we ready to move on? All right, so how do we experimentally determine these coefficients? That's where we're going next. And this is determining rate law. If you're interested in reading about it in the big black book, this is section 14.2. Okay, and this is called the method of initial rates. What does initial mean? The rate at the very beginning. And why are we using the rate at the start? Because at the start of the reaction, we know the concentrations, yeah? Because we have this thing, which is this concentration, that thing, which is that concentration. We mix them together, and if we can measure the rate in that instant when it first starts, then we've got, like, we know the rate at particular concentrations. Yes? Okay. When the concentrations are known. We are going to look at two experimental methods. One is this method of initial rates. And then we're going to look later at a graphical method, which is also known as the integrated rate law. The good news is if you know no calculus, you don't need to in order to have the integrated rate law. Here, we're only going to look at method number 1, and we'll leave method number 2 for the next section. All right, so method number 1. If you increase the concentration of A, and you'll notice we call it concentration of A, and what's that little thing down at the bottom? That is a 0, that is a naught. So in other words, that is the initial concentration. So A with that little 0. You don't have to put the line through the 0. You can just write concentration of A with a little 0 at the bottom. That's fine. So if you increase the initial concentration of A and the initial rate does not change, what does that tell you about the order with respect to substance A? You change the concentration of A and the rate does not change. Does that mean that rate is equal to K times A to the 0? Does it mean it's equal to K times A to the 1? Or does it mean that it's equal to K times A to the 2? If rate doesn't change, which of those three things is true? Which one do you guys like? First one, right? Because what it means is that rate is just equal to K and does not depend upon concentration of A. So you can change concentration of A all you like and you don't affect the rate. Yes? Okay. If you can increase the initial concentration of A naught, and the rate increases, then A will be in the rate equation. So it'll be A to the 1 or A to the 2 or something like that. So you will have a non-zero order with respect to A, and so you will have A will be in there, and then you just have to figure out the exponent. So basically what you're going to do is you're going to run a couple experiments. You'll run it at 1 molar as your A naught concentration. And then you'll run it a second time where A naught is 2 molar. And you'll say, does the rate double or does it quadruple? Does that make sense? So you're going to change the concentration of the initial by running 2 experiments. You'll have your initial, and then you'll have your second initial. It's better if we have the diet. You know what? We're just going to go ahead because I have it better laid out here. We look at our A naught values, and in the course of the experiment, we change the initial concentration of A. If we double it, that means that was times 2. If we triple it, that means it was times 3. If we halved it, that means it was times a half. And then we say, by what factor did the rate change? Did it double? Did it quadruple? What happens? And then we say, how do these 2 factors relate to one another? So if I double the initial concentration, and I also get the rate doubling, what's our exponent? These are the same, and that means our exponent is 1. So this is first order with respect to A. So our rate law would look like rate is equal to K times concentration of A raised to the power 1. If you double the concentration of A, the rate will double. And I think, yeah, that's good. Okay. Now, let's say we double the concentration of the initial concentration, and the rate quadruples. So what we're looking at is we double that, and then the rate quadruples, which is the same as 2 to the 2. This 2 is that 2. That tells us that our exponent is 2. If you double concentration of A, the rate will quadruple, and that's if you have a square up there, and that's second order with respect to A. Although you will not come across them very often, it's possible you could. If we double the concentration of A, our initial concentration of A, and that gives us an octupling of the rate if the rate increases by a factor of times 8. 8 is 2 to the 3. And so that means that it is going to be third order with respect to A naught. So if we look at these little tables, these kind of summarize it for you. If we double the initial concentration, if the rate remains unchanged, it's 0th order. If the rate doubles, it's 1st order, and if the rate quadruples, it's 2nd order. If we triple the concentration, if it remains unchanged, it's 0th order. If it triples, so if it does the same thing, that's 1st order, and if it goes as the square, that is 2nd order. You should also be able to look and say, what happens if we half the concentration? If we half the concentration and nothing happens to the rate, that is 0th order. If we half the concentration and the rate does the same thing, it is also halved, that is 1st order. If we half it and the rate is quartered, because that's a half squared, right? Then that is 2nd order. How on earth do we use these things? You are usually given a data table. Okay, and you'll be told we have experiment number 1, we have experiment number 2, we have experiment number 3, and you will be given the initial concentration of A in each thing, and you will be given the initial rate for each thing. So as we move from experiment 1 to experiment 2, what have we done to the concentration of A? We have increased it, we have multiplied it by 2. What has happened to our initial rate? It has also multiplied by 2. If you have trouble seeing that, you can always take 9.6 times 10 to the 6 and divide by 4.8 times 10 to the 6, and you'll get 2. Yes? Now, if these are the same, then what's our exponent? Yeah, so our exponent is 1. Because if I double the concentration and I double it and that doubles the rate, that means our exponent is 1. So our order with respect to A is 1st order. And if we had to write the rate law for this, what would we write? What's the first thing we write? Rate equals constant, concentration of A, and then it's up to you whether you write the 1 or not. Okay? So you could either do this, or you could just write rate is equal to K times concentration of A. I would probably not write the exponent 1 just because it's a little odd. This is probably better. Okay, so there's an answer here, blah, 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 blah. Now let's examine the 1st and the 3rd experiment. So now we're going to say what happens as we go from 1 to 3. What have we done to our concentration of A? We have multiplied it by 3. Based on our previous result, what would you expect to happen to the rate? You would expect it to times 3, and in fact, it is times 3. Okay? What if we have 2 reactants? You have to look and say, I need experiments where I am only changing one thing at a time, okay? So if I am looking at experiments 1 and 2, what am I changing? I'm changing the concentration of A. And what am I doing with it? Multiplying by 3. And when I multiply by 3, what happened to my initial rate? 72 divided by 24 is 3. Oh, so what order are we with respect to A? 1. Which two experiments should we compare when we're looking for reactant B? Yeah, we could do the first one and the third one. Why wouldn't we use 2 and 3? Because we're changing both concentrations. That's useless to us, okay? So for B, we're going to use our first and our third. And what happened to concentration of B between the first and the third? We multiplied by 2. And it is important that these two are the same, right? And it is important for the red one that these two are the same. All right, what happened to our rate when we doubled B? Same. Which tells us what order is it with respect to B? 0th order. So what is the rate law then for this equation? Rate is equal to K times concentration of A. And you can put a 1 if you want to. I'm going to leave off the 1 now. And what do we do with B?
It cancels out.
It cancels out because it's just nothing. So that's it. That is your rate law. Okay? And this just walks you through it. Blah, 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 blah. And we are almost out of time. Yeah, we have 5 minutes. We can do this. Finding the value and the unit of the rate constant K. So this is on page 8. In these problems, you might also be asked to determine the value and the unit of K. So to do this, you will take the rate equation and you will solve it for K. Then you'll take any of the experiments. It doesn't matter, experiment 1, experiment 2, experiment 3. You will take the concentrations from that and the rate from that, plug them in, and then you'll get a value for K. And you will also get a unit for K. So, for example, in experiment 1, from here, right? And this was our previous one. So our rate law was rate is equal to K times the concentration of A. And we're going to use experiment 1. So we're going to solve for K. K is equal to rate divided by concentration of A. And then we're going to plug in the rate, which is 2.4 times 10 to the negative 4. And I am lazy, so I'm going to write moles per liter as molar. Molar per second. And then that's going to be divided by the concentration of A, which is 0.01. And that is the unit for concentration of A is? Unit for concentration is? What's a unit for concentration? Molar. There we go. Molar. Look at that. Our molar is going to cancel out. And we will end up with 2.4 times 10 to the negative 2. What is our unit? What unit is left? Seconds? 1 over seconds, or in other words, seconds to the negative 1. Okay? So rate constants can have weird units, okay? And you just have to plug everything in and make sure, like, just cancel out what cancels out. Alrighty? Your homework is from the Green Book. Green Book. Pages 96, 97. And 109 to 111. Do you guys feel like you need more practice with potential energy diagrams at all? No? Okay, then I'll leave that. And other than that, just study for your quiz on Wednesday and do the review.
Yeah.
Yes, that's on 1.3, 1.4, 1.5.
Tomorrow, I mean, so we 5 tomorrow. No, because I was confused about it. I don't think like it gives me like the bubble chart and I'm like I don't know what do they have because their glucose level was high and I was like this is
That's good.
huh?
Oh, absolutely. Yeah, just let me stop